So, okay. I don't know about the exams. Okay. Anyway, we are recording. We'll start the session now. I'll see if there is a need for extending the homework, but at this moment, I'm not 100% sure if there is a need. But attend the PS sessions on Friday. Ask questions about the homework there as well. So let's go back to this thing. And we said this structure definition, actually, once you declare a variable of a certain structure, then the memory allocation will be kind of it will be a consecutive allocation of memory as if you have 5 different variables, one after another. Okay, this is very simple. All right. So the you can have also a hierarchical definition or hierarchical structures, meaning that you might have a structure that can have a component which itself is actually obtained using a structure. All right. In this case, you see an example here. My first part of my struct is a basic type, the first part. The second part is actually another struct, another structure. And the third type is anything, a string. So this means that within the struct definition, within the structure, your individual components can be of any type, including another structure, right? So there is no limitation regarding what you could have inside, except that the only limitation is when you actually declare a part of your structure, like using a type name, right? You will use a type name and then a name for the component, right? So this is the regular way of doing this, or correct way of doing this. This type name should be defined at that time. When the compiler reaches here, it should have already seen this definition. The definition of planet T at this location should be available, right? If the planet T is not available, the compiler is going to complain. It's going to say, you are trying to declare something of some type, but that type is not available to me. I don't know what that type is, right? So this type, and this is an internal type anyway, it is available, character is available, but this type is a user-defined type, and it's supposed to be declared somewhere up here before this type struct starts. It should be somewhere up there and defined. This is very important. All right. And then, so how do you access, let's say, the parts of a given struct? So I have planet, let's say, current planet, which is defined to be planet T of type planet T, right? Then individual components can be accessed by putting a dot after the variable name and the component name itself that is actually appearing in the structure definition. So if you recall, the structure definition was simply this. So you have character name and then diameter, moons, orbit time, and rotation time. Therefore, given a planet name like a variable like this, so my planet dot name will access that entry here. My planet dot diameter will access this name here or this variable there and so forth. This is the way that you access them. And you can use that access for both reading a value from that place and writing a value to that place. Writing a value to that place means you actually use that variable name dot component name as on the left-hand side of an assignment statement, or you send the address of that thing and actually use that address for an indirect assignment to that location. All right. So you can, as you can see examples here, you can use it as an argument to a function. You can actually use it as a left-hand side argument to a assignment operator, and so forth. Okay, and you can use it as a value, of course. This is obvious. Okay, you can manipulate structures. So you can change the structure name. You can not structure name. The value stored in a given variables component for that particular component. You can change the value there by doing this type of an assignment. All right, this is easy. You can use structures as arguments. Now, when you use a structure as an argument like this, as you had here, what happens is that if you use a structured variable as an argument, is passed to a function as an input argument, all of its component values are copied into the component's function corresponding the formal parameter, if you recall. So let's assume that we have this PL. PL is my local argument, my argument here. This is PL, and assume that this function is called using another, let's say, planet T, and let's say it is X, and X is, let's say, planet X with 0, 0, 0, 0 entries, right? Now, when you have this one, there is going to be a local copy of PL here, and the entire entry of this guy is going to be, when you call this function using X, it's going to be copied here. So PL will have a copy of each entry, each component of that structured variable, right? So each component. In this case, there will be a string copy followed by a copy of a floating point number, a double number, and an integer and two double numbers. So then what you can do is, after this copy, you can use those values as a copy of the original argument, or the formal argument, and you can perhaps use their values, but there, if you actually do any type of a change in this local copy of that, so for example, if you change the PL.diameter using an assignment statement, that will be not reflected back on X, because you would actually be just doing the changes on a copied version of that variable. So it's not a it's a copied. The values are copied as you would have seen this, or we have seen this when the argument is, let's say, one of those basic types like integers. If you have an integer X as your argument to a function, local changes to that argument is not going to be reflected back in the callee side. The caller is not going to actually have this thing change. So you can see an example here. We have an equality function given two structured values. So this is planet, and this says, okay, if two planets are supposed to be the same, perhaps their name should be the same, as well as their diameter, their moons, their orbit time, and their rotation time should be the same. You cannot say that, for example, oh, I'm going to say planet 1 is, can I check this guy like this? The answer is no. because double equal sign for comparison is only defined for certain things, basic types like integers, doubles, and characters, and maybe enumerated types, and that's it. So basic types, integers, floating point numbers, and characters. Not even strings, not even, let's say, arrays, and certainly not for structures. So structured values cannot be compared using double equal sign comparison operator. So this operator is only defined for or available for your basic types. Okay. Now the question is, what if I want to actually output my changes in the function, in the called function, and I want to actually make the changes available to the caller, right? In that case, as we have done before using pointers, we'll use a pointer. And we'll actually use a pointer to the structured value or structured argument, structured variable that you have in your caller, and you will send the address of that to your function, and that function is gonna actually, when it actually does anything, a change in that in the components of that variable or structure, then it will be reflected back in the original variable. However, you have to be very careful. There are two possibilities of actually using this one. So as you would recall, this pointer to, let's say, planet like this variable, we can actually use it like this, and then dot will actually get us the, for example, the name. So I will still do pointer, the variable name, and dot name. So I'm putting this parentheses just to make sure that I'm not confusing the dot name with an address of like a pointer to PLNP name. This will be later important. So this is not what I'm intending. This is what I'm intending. Okay. Now C says this is kind of cumbersome to do. She said, okay, if I'm gonna do this a lot, because I'm gonna actually try to change the values of a structured argument, right? So how do I do this then? Instead of actually doing this parentheses and then two parentheses, open and close parentheses, and then star, C says there is a simpler way of handling this one, and that simpler way of handling it is, where am I? I have it here, this way. So if you have a structured pointer like this, and this is how you access it with a point and then component, you can actually do the same thing with this guy here. So pointer name, pointer variable, and an arrow. Arrow is in this case a minus sign, and also simple greater than sign. So struct pointer, arrow component will actually be the same as within parentheses star struct pointer dot component itself. So this is kind of a shorthand use of the above thing. All right. So this is important. This will be, this is common that we are going to use this a lot. So when you have a structured argument, when you are actually, let's say, just passing the argument using copying, then you are going to be, let's say, if I have a function foo with, let's say, a structured type here, and if I have x, for example, for this guy, then x is going to be accessed, the component of x is going to be accessed using the point dot. So dot name, for example, right? If this is a pointer, which allows us to actually change the components of this variable, then this is not going to be the case. This is going to be the case. An arrow following the variable name, pointer variable name, is going to actually give us access to individual components of that record or of that structure. All right. So this is a shorthand, kind of a easy way of accessing this type of. So now you have to be careful. For example, let's say when I have, let's say this is now that I know it's a pointer to a structure to the variable. Now I can access the parts of that thing using an arrow. But in some cases, I may be able to actually just use that as a pointer to something else. So if I need to access this pointer to this guy, or the pointer to this one or this one, what I will do is I will use an ampersand sign. Ln P is my variable name and diameter, like this. So usually you might want to actually put a parentheses type to make sure that you are reading this ampersand sign to be actually the entire thing, or you can actually ignore the parentheses, because here you know that the arrow sign actually takes the priority, and it says, okay, arrow sign says orbit time is Ln P's part, and then I am actually taking the address of that orbit time for that particular variable, structured variable. All right. So we are going this quickly. We are gonna, very fast. We are gonna come back again to details of these things. So if I want to return a structured result, a value, I can simply actually create one here, and then fill it in here, and then return it here. If you recall, return will actually do a copying operation. So it will copy the individual components of planet to the target one. The function that you are going to actually say, okay, planet P, when you call this function with x, and x equals get planet, this will be actually doing the copy, whatever. All right. So you have to be careful with this. Okay, so get planet will actually return this thing and copy it here. All right. So let's actually look at a simple case where we are actually using, let's say, we want to keep the time of the day. All right. So the time of the day is, it has actually 3 components. You cannot actually just simply represent the time of the day with a single value, right? There are several ways of doing this. One way would be, I would actually use 3 different values to keep the day, time of the day. First value is the hour of the day, and within that hour, the minute, and within that minute, the second. And these could be simply integers. Okay, this is proper way probably to do that. Now, instead of keeping 3 variables for keeping the day of the time of the day, you would actually create a simple structure as we have here, and call this as time type. And now time type can actually, a variable of time type can keep the time of the day. These 3 types of values can be kept in one place. Of course, you can say, oh, you know, I can do this with a string, like this one, for example. You can say char and say, okay, here, I don't know, time. Let's say time, and it is 20 long string, and you say, okay, here 2 digits for hour, and 2 digits for the minute, and 2 digits for the second, for example. Yeah, this is possible, but this is not as obvious as this guy. This is, you have to actually have a kind of a conversion routine to actually go from string to numbers and then so forth. This is neater in this case. Okay, so for example, this says, okay, I wanna get a new time from, let's say, from this function. This is the function definition. So you have a given time of day, and then you give actually, let's say, elapsed second, the number of some seconds actually after this. You say, okay, my current time was this. What happens? What time it would be if I actually have, let's say, 1500 seconds later. So this will actually give you the new time. And the way that you would do this one, of course, is very simple. You say, my new hour is going to be, first of all, I'm going to look at the new second. My new second is going to be time of the day second, given time. So let's say that today, right now it is, I don't know what time it is, 2:58 p.m., right? So forget about, if we want to do this with a 24-hour thing, it will be 14, 50, 28, and the second is, let's say, 02. And you say, okay, there has been, let's say, 100 seconds passed since this. So what you are going to do is you're going to take this part. This is, you can get this part by saying the current time dot second. So current time dot second is going to give me this part. You add to this one 100. Now you have 102 seconds. 102 seconds is not a proper number for this one because the second part of that thing should be less than 60. So you do a modular 60, you get your second, and the remainder of that is going to be your minutes that you need to add here. So you take this thing, you do a modular 60 to this one. This is your seconds. The remainder, the number of times that you actually have that many minutes, you add the minutes here. And then you do another modulo for this guy because this cannot be more than 59. It could be at most 59. So the rest of them are gonna go as an hour here. So you add you get your seconds, you add your seconds here to minutes, and then you have you get your minutes, and then you get your hours to this one. Perhaps at the end you may want to also do another modulo so that you actually get the time of the day. And you don't care about if it is 2 days later or 5 days later, you just care about the time of the day, right? So this is one way of actually updating the time, current time after, let's say, a number of seconds. So, and this is how we actually did it. So what this guy does is actually it takes, since the call is just a regular definition, so this will actually copy the entries of the current time to this guy, and it will actually do everything inside here. And then now the time of the day is actually updated, but the caller hasn't updated yet. Then I have to return that to the caller so that the caller can update its own copy of the variable, of those 3 values. All right. So I could have actually done this the other way around. If I want to actually do it, let's say, with a pointer, I could have said, okay, forget about this part, forget about this part. Just assume that this is actually requiring an address now, and send an address to this one to me. And then now here it is an address, right? And then each of these dots becomes an arrow here, right? And each of these dots will become an arrow. And then what I will do is I will just forget about the return because the return is going to be automatic. So you can see that if you have a complicated record or complicated structure, you're copying 2 times copying from here to here, and then from here back to the original one is going to be quite costly. Copying costs in terms of time. It takes time to copy things, and the larger the number of things to copy it, more than time that is going to be required for it. Therefore, your efficiency, which will be usually your program efficiency, your algorithm efficiency, will be usually measured by the amount of time it takes to actually do your job, then it will be suffering because of those copying. So you may need to actually be careful if you want to actually do this type of things. Of course, this has a disadvantage. If I actually do something by mistake, if I actually use a pointer here and do something by mistake here, it will actually update my calling variable. The actual variable will be updated. So that might not be as, let's say, as desirable. In those type of cases, perhaps what you do is you say, okay, if I want to actually send a function, I want to call this function, let's say, foo, with my, let's say, time t, as a variable, an argument. I want to send this as a pointer, because I don't want to actually copy it, because copying takes time. But I don't want this function to touch this either. So what do I do in that case? If I want this foo function not to touch, not to change, it will touch it, but it will not. I don't want it to change my input argument. What do I do? What is the answer? What do I do in that case? So questions. I have a question first, and then I will read your questions. So what I'm trying to do here is I want to send my function values, but I want to send this as a pointer because I don't want to copy the values. Okay, so this is the way that I do it. This is the way I should do it, using a definition like this, pointer definition. But this doesn't guarantee that function foo will not change my entry. Whatever I actually send here, function foo can change it, but I don't want it to change, because function foo is not supposed to be changing that for its because of its definition. So what do I do? We actually put a const in front of it. This will say, okay, I'm sending you a pointer to access to this guy, but you are not allowed to actually do any changes, meaning you are not allowed to do, let's say, a change that involves pointer something equals something like this. So your components of that structured pointer is not going to actually be an argument, a left-hand side argument to an assignment statement. All right, we are going to come back to this one again. So there are some questions. Eren is asking, can a struct contain itself like this? Now, this is a good question. The answer is, with this definition, no. Why? Let's see why it is not possible. Let's get maybe an empty page here. Let's see. Let's look at it here. So Eren's question is this. I have, let's look at this one, what he has here. The same thing. I have type def, and I say, okay, struct. And I have some, let's say, integer a, and then this s name, this s name, struct name, b, and he's saying that let's name this struct as s name. And is this allowed? This is what he's asking. The answer is no, as it is. Why? Because look at it here. The compiler is going to come and starts here. Compiler is at this stage. Compiler is not very, very smart. Compilers are very, very dumb. They will do things one at a time. They will read things one line at a time, and then they will try to see what is happening afterwards. So it will come here, it will know that actually you are trying to do a type def of a struct. So this is fine. And it says, okay, this should start with a curly braces, and it should end with a curly braces. It knows this one. Now it will check what is in between, and knows that in between there will be some type names and some component names, right? So the first one is easy. This guy is easy. This part is easy. It's an integer a. and I know what an integer is, I can define a name A for this one, and then I'm done. Now let's look at the second part of this thing. The second part says S name B. Okay. Now the compiler is going to say, what is S name? Do I know what S name is? At this moment, no, I don't know it. When am I going to know it? I'm going to only know it once I actually finish up this part. And then I'm going to know it that actually that's a name. So at that stage, in this code sample, since S name is not defined, the compiler is going to say, no way. You cannot define a component in your current structure and name it S name, because I don't know what S name means. Even though you know that you are intending to recreate it later on, like a recursive definition, this is not possible. The compiler is not smart enough to understand or predict that you are going to actually use that name. Now, okay, the question is this might be a bad restriction. This is going to say that I cannot do a recursive definition. And we have been saying that recursive definitions are good, recursive stuff are good. So why don't I do actually recursive definition? We are going to see that C is going to actually let us do this in a different way, not exactly this way. It will actually let us do it in a slightly different way. It will change the type of struct, this declaration slightly, so that we can do these type of recursive definitions. But the one that Eren is saying, or I hope I didn't forget his name. Yes, Eren is saying is not possible. There will be one other possibility. Okay, Gökbey answered my question. Const, yes, it was right. Good. So there is another one. 17, page 17. Tekrar anlatabilir miyiz? Page 17. What is page 17? Which one is this? Okay. Of course, we can repeat this part. So we said if I have a function, let's say I have a function integer foo, and I have, let's say, let's do it here a type def struct integer x and y, and I call this as a point. A point has two integer values, okay? And I'm saying that PT is, my current point is something like this. This is a function. The question is, how do I access the values of this P? One way of doing it is actually this way. This is X. I'm accessing the X component of P. This is accessing the Y component of P. And C is saying that this is proper, this is correct, but this is, writing it is a little bit difficult. Why don't we make it simpler? And the C's way of making it simpler is, C says, okay, you can do this one for sure, but I'm going to allow you to do this another way also, another alternative. And the alternative is doing it this way. P arrow X will actually be the same as this one, meaning the pointer that is pointing to a type, structure type PT, the components can be accessed using this. P arrow X will give me the pointer that is actually pointing to a structured type and the X component of that type. And then this one is going to go for the same component or different component of the same variable or same value. So this is just, they are just alternatives. You can use either of them. This is a little bit easier to read, but this is correct as well. This is the proper way. I mean, this is the theoretical correct way. This is what C is allowing you to do instead of that theoretical way. All right. Good. Let's see. We have 8 more minutes. So the idea of this type of, let's say, values, this combining basic types to actually get new types is can be actually considered under the topic of abstract data types. An abstract data type is a data type combined with a set of basic operations. So we usually, in this case, we just don't actually provide what the type, let's say, types, the components of the type is going to be, but also some sort of a way of operations to manipulate our own data types, right? So you say, okay, I have time t. We did this one, right? We say, okay, I have an abstract type. I said, okay, this is struct. We said type def struct, and we say integer, hour, minute, and second, and we said this is time t, right? Now, this is only defining the values that you can have. The values here are combination of 3 integers. And there are some other things that we are actually saying here, like a minute cannot be larger than 60 or 59. Second cannot be larger than 59 either. And hour cannot be larger than 24 if we are aiming for a 24-hour, let's say, kind of a representation. Right? Now, the question is, that an abstract data type has 2 parts. One part is actually how do you represent your values? Like a time t can be an abstract data type. But you need to know, first of all, the values that you can actually represent. The second one is also the operations that are allowed on this type. So for example, if you give me 2 time t variable values like t1 and t2, can you actually define, for example, an addition operation to this type? Let's say a subtraction operation, a print operation perhaps, or a multiplication operator if it makes sense. I don't know if it makes sense in this case, but so these type of operations that you can actually define on top of your values, you should add, you add them as part of your abstract data type. And when you do this one, now you have a complete data type. We call this abstract data type, where you actually let us know what type of values you might have, usually a combination of different basic values. And then on top of it, what type of operations you allow on those types. When you actually define these things, you define now an abstract data type, which you can actually now send around and people can use that. So if you actually tell me, for example, time t has your functions or operators like, let's say, addition, perhaps subtraction, right? Those type of, or maybe adding some seconds to it, hours to it, and so forth. If you have all these things defined, then I can use that in an abstract data type without knowing the implementation details. I can use it for my, let's say, algorithm needs. This is an important topic, and abstract data types are going to be also quite important later on when you look at other programming paradigms like, let's say, object-oriented programming and so forth. But the idea, basic idea is a data type doesn't just involve the values, how to represent your values. It also involves what type of operators are allowed on top of those values. And if you can actually just define these functions and give it out, then you are creating an abstract data type. People don't need to know exactly what things are happening there, but those operators will let you get a kind of a conceptual concept or an abstract idea what things are or what is happening with your data and what you can do with your data. For example, perhaps for planet T as an abstract data type, you might need, for example, an equality operator that given two planets, can you check if one planet is the same as the other one? Perhaps you might have another operator, for example, for printing your planet. Once you actually provide me this function, I don't need to know. I don't need to worry about again doing a printing of your values of this abstract data type. Again, perhaps another function could be, or operator could be, reading something from the user to actually some planet from the user and some other things perhaps. So this is the idea. Now, this abstract data types can be implemented using structs. So in this case, what you're going to do is you're going to define your planet T as for the values and those functions that you want to have as part of your abstract data type. All right. For example, there's an example here. This is complex numbers. Complex numbers can be treated as we have, for example, we actually know an abstract data type already. For example, integers. Integer is an abstract data type, and we know from C that integer x can actually define an x, and if y defines an y, and x plus y is an operator that actually adds them up. X minus y is another operator. X equals y is also another operator. X double equals y is another operator. X bigger than y or larger than y is another operator. Those type of operations are already defined for this integer type. So, for example, if I want to do similar things for a complex type, there is no internal definition or internally available defined type, abstract data type for complex numbers in C. Why do we have for it integers and but not C? Because integers are very, very common. You cannot do anything without integers or without a double number. Therefore, it makes sense to have them as language defined, not user defined. But some users might want to use, let's say, complex numbers. In that case, I will take a complex number as defined like this. It has two double parts, meaning two double precedent floating numbers, real and imaginary. And then now, complex numbers have a bunch of operators that I know. For example, one operator is I can add two complex numbers. What do you mean by adding two complex numbers? I have first complex number, the second complex number. I add them, I return you a complex number, a new complex number. You can do subtraction of two complex numbers. You can multiply two complex numbers. So if a complex number is, let's say, R1 plus I1, let's say, imaginary one, J, like this, and a second complex number is R2 plus I2 times J, right? So C1 plus C2 is very simple. You actually add the real components, and then you add the imaginary components and return the new number. This is the definition of adding. Multiplication is the other way around, right? When you multiply the imaginary part of the first one with the second, or real part of the first one with the second part, and so forth. So all these things are the things that define a complex number. When you actually give me this entire thing, now you have given me an abstract data type. I can actually now, once you have defined and actually implemented those functions, I don't need to even know what those functions are doing. I can just use their names to actually carry out complex number operations. All right. So this is an important thing. We are going to work on this one quite a bit. Now you can see that once I actually have those libraries available to me, then I can actually just define two complex numbers. See, I don't need to know how it's actually done. I can read it from the user. I can read another number from the user. I can add them. I can print them. I can add them, and so forth. So here you can see that the user of this complex number, this complex type, and the functions provided with that has nothing to worry about. He doesn't need to know anything about how a complex number is defined. Is a struct with two integers? Is it, let's say, a struct with two double numbers? Or is a floating point number? Or is it, let's say, an array? I don't care. So you could have actually done it this way. You could have said type def, okay, let's say integer 2, or not integer, double 2, is your complex T. So you can define your complex number to be a two-dimensional array. That's a possibility as well. But once you define all these functions like that, you don't need to worry about that anymore. So the user is going to be just doing this, what we have seen here, what we are seeing here, right? He doesn't need to know what complex T is, how the structure is. He needs to know only the functions to read them, functions to print them, functions to add them, and whatever. So this type of abstraction is very, very useful in programming. So one person can write this and put it out there, and then 1 million people, programmers, can use this without the need to actually understand how the implementation happens. So the implementation details are hidden from you. This is going to be very, very important when you actually see the object-oriented programming. This is one of the places where there was a question, are these structs similar to things, classes in object-oriented programming? The answer was no, but the concepts you can use, actually, you can create abstract data types using these as well as some other object-oriented programming techniques, right? So here we see that structs can be used for simple or abstract data type creations. All right. And then implementation of this one can be done by let's say, whoever is actually designing the internal structures of this data type, the values and so forth. Questions? I think we have run over our time. Any questions? So we'll continue with this topic tomorrow at the same time, 1:30 tomorrow. If there are no other questions, I'm going to stop the recording. And